Okay, now let's continue. This is there are actually four distinct steps to map an algorithm. Okay, four distinct steps. So the input, of course, would be your point cloud, and then the distance matrix will be computed in the map algorithm. So once we have the distance, then we would be able to do these four steps. So the distance can be in the context of zero distance, which is a kernel also, right? Any kind of a metric or measure which would be able to elucidate the structure of your data, right? Anything actually. So delta can be anything, preferably a distance matrix, of course, right? So the first step is to create a filter, right? To create a filter. Again, as I said, you need to know to a certain level of your data, right? You need to know a certain level of your data. So this map algorithm can be classified as semi-supervised machine learning, where you need to know about the data to a certain level. So you get to choose a proper filter such a way that you get to elucidate the structure of the data, right? For example, let's say we don't know the structure. This is in a high dimensional space. We can simply choose one feature, right? For example, if I choose just like one feature, X value. So I can just choose the X value as a feature, as F here, filter, right? X value as a filter. And then this X, the filter would be it's of course your data set. So I choose just X value, and then then I'm going to create cover. Cover simply means take that X value. For example, I have my X value here. I break them into 4 connected intervals. Yeah. So 4 connected intervals I can see in red, green, blue, and orange. These are all X values actually, just X values, right? So red, green, blue, orange. So these are my cover. Taking X value and breaking them into connected covers. So connected here simply means, as you can see, there is an overlap. At this overlap, actually similar X values. That is when, so if you would choose such a way, then your filter, right? Your filter, which is the union of all these covers, which you have now 4 covers, is path connected. Path connected. Because why? You choose in X interval, an X interval and Y interval are actually overlapping on top of each other, which means some X values are being used in red and also being used in blue, right? That is called path connected. So that's the first part. So first part, choose a filter, and of course from this filter create covers. So you have here 4 covers. The next is pullback. So once you have the cover, you want to find corresponding points of this cover. For example, right? So for example, this green cover is actually corresponds to all these points in its space, right? That is the green cover here. Whereas the red cover, the first V1 is the red cover, is corresponds to this red color, red highlighted area and its corresponding points. Of course, there are overlaps. Yeah, there are overlaps in between. There are overlaps in between this blue and red. In fact, I just like probably all these points and these points are same points. Yeah, the same points, because why? It is path connected. I just like put it separated such a way that you get to see the red points and also the green points. So this is called pullback. The pullback of the cover, right, induces all those original data points. Okay, so that's pullback, second step. The next step is clustering. So each cover is considered as a a data point. You can assume it's like a sub data point, right? Taking the data point, you do a standard clustering. Yeah, you can do a standard clustering. So you have learned a clustering. You can do any type of clustering and do clustering for all those cover. So now, first of all, the pullbacks. Yeah, the pullbacks now we denote as UI. The cover was VI. The pullbacks. Yeah, the pullbacks are all these are UI. Yeah, UI. So for UI, you do clustering. For each, you do clustering. Once you have clustering, now if right, if the clusters, right, if the clusters intersect, if the clusters share same point, then we draw an edge. So what it says is that cluster UI intersect cluster VI has some value, right? This here, if it's not empty set, if it's not empty set, simply means has some value, then we draw an edge like that. For example, red and green, they overlap. Yeah, they have some values. It's not an empty set. Then we draw an edge. So similarly, we draw an edge for blues. So basically, these blues, I should color this a different color. Yeah. If it's the same color, it's going to be just one point. Yeah. And then orange. Okay. So you get to elucidate or visualize the structure of a given point cloud. So these are the 4 steps. First is the filter function. You choose the right filter function that you think would be able to discriminate or illustrate the pattern of your data. Second is the pullback, right? So for every single cover, it's going to have a pullback, which is now from V, we get UIs. UIs are now the pullback for each cover. After that, do clustering. Once clustering is completed, when the clustering has overlapping points, then we draw an edge. Okay, so 4 steps. Now let's look at an example. Okay, before looking at example, let's just look at the free parameters that we have. Free parameters that we have that which we can customize the network or mapper graph. Right, first is the type of distance that you want to use. Since it is one of the input for map algorithm, any kind of distance for that matter that we have discussed in the lecture. As I said, it can be also a kernel distance or pseudo distance, which does not really satisfy the axioms of being a distance as well. As long as you know upfront that it would be able to elucidate the structure, then please by all means use them. Right. Next is filter function. So previously I just simply used an X value. So filter function can be anything for that matter again, right? Again to elucidate the structure. So for example, so the filter function also can be in any dimensional space. So given a filter function, it takes the input of your data and then you create a filter function. The filter function can be any dimension. For example, the dimension that we used earlier is just d equals to 1. One dimension is just a line. So you break them into small covers, right? Overlapping covers. Whereas it can be also d equals to 2. So you get area, like a cubes, right? Cubes. And then d can also be a 3. Then you get a nice box like that. Right? So it can be any dimensional space, but usually we use a lower dimensional space, right? So that it is easier to compute. So we can use d equals 2, d equals to 1, d equals to 3. Okay, so that's the first thing, filter function. And so again, the filter function itself, right? Just now I used an x value. You can use y value. So if you use x value, it is called a width function. So it goes from left to right. Because if you use y value, it can be a height function. It goes from bottom to top, right? It can be a height function, which is just a y value. Or it can be an output of a dimension reduction, the first PC. So I say PC1. It can be 2 PCs, PC1 and PC2. It can similarly be at the output of TC as well. First output, second output. Can also be MDS. Yeah, all these are dimensional reduction methods, right? And then the distance, right? The distance can be similarity, dissimilarity measures as well. So L1, L2, cosine is similarity measure, can also, right? You can also use each single point. Yeah, for each single point, we could be able to compute its density. And density basically would take into consideration the members or the neighborhood, right, where it lives. So that is density. It can also be eccentricity. Eccentricity again measures the distance from a vertex, or here it can be a sample point, to the farthest other vertex. So what it does, essentially, it quantifies how central a vertex within a graph, or in your data set, a point within a point cloud, with lower eccentricity values indicating a more central position. So an example, right? An example, how far is this point to the rest of the points, right? Or the furthest point, right? For the eccentricity. Whereas density, the neighborhood, right? How dense it is, right? So these are the potential filter functions that you can use. And then number of covers. Previously, so I used like just broke into 4. I take filter function, broke into 4, and I call each as V, V1, V2, V3, V4. These are all covers. We can also call intervals. And then gain. Gain is the overlap. Yeah, overlap that we use. We need to overlap the covers such a way that it is path connected, right? For example, 30%. I'm going to overlap V1 and V2 30%. So you get to set that as well. That's called gain in map algorithm. And then after that, yeah, the third step would be on clustering. So after you do a pullback, yeah, you have your point cloud. I mean, you have your cover. For each cover, you get to pull back, and then you get your point cloud, corresponding point cloud, and then you can do clustering for each. So once the clusters intersect, then you draw a line, okay, which is the edge. So you get your mapper algorithm. Okay, so let's look at an example, a toy example to illustrate, to make sure you understand how it works. Now we are going to do for each. Right, okay, now let's assume we have a 2 circle. Yeah, we have seen this data set a numerous times now. So it is in R2 with some sort of noise, right? And then of course we have like 500 points. The hex is we have 500 points in R2, right? And then of course each has 2 features, X and Y feature. So I'm going to take first filter function as X value. So as you can see from left to right, it has been color coded, right, based on X value. So we're going to use this X value as our filter function. So we take our function, filter function, takes the X basically in R. Yeah, this is actually just X value. Originally it was X and Y. Okay. Now, so-called width function, because Y is taking it's considering from left to right, becomes a width. If you were to take the height function, basically you're just taking the Y value from below to top, right? As I said earlier. Okay, we are going to use the width function, which is just X value. Now let's look at first class DB scan. Yeah, you still remember DB scan? So DB scan has 2 main input. One is the epsilon. Next is the minimum sample. Yeah, nearest neighbor. The minimum sample that we need to consider to do clustering. So of course, this data set comes with label, right? So first circle is now is yellow, and the next smaller circle is in purple. Yeah, 2 distinct colors clusters actually. So we are going to compare it, how it behaves. This cluster, DB scan cluster behaves in our map algorithm. Right, first step. Yeah, so I've chosen my filter. A filter is just like my line. One cube is just a line, right? I have chosen. I want 5 covers. So I have V1, V2, V3, V4, and V5. And I gain is 10%. So I'm going to overlap each other in 10 for 10%. So they are overlapping 10% of each other. And next is the pullback. Yeah, the pullback. Of course, it is going to induce point cloud. So we have corresponding pullback. So each cover is now by chance. Yeah, each cover by chance corresponds to one pullback, which is U1, U2 until U5. See, U1, you have U2, U3, U4, and U5. So I've colored here for you to see. So each will be a so-called a sub point cloud in which we are going to do DB scan. Okay. So once you do DB scan, you would then, you see, they are overlapping. So C1 is the first cluster. We are overlapping. So they are overlapping. They are overlapping to each other. So you end up getting a mapper graph as such. Yeah, by U1, U2, U3, U4, U5 corresponds to the clusters. So it, by chance, every single pullback became a cluster actually, right? Okay, here, that's step 3 and step 4. Yeah. So we have every single pullback is now correspond to one cluster. So since the clusters they overlap, then we have the edges. So you end up getting this mapper graph. Okay. Of course, it did not really represent the structure of a given two circle, right? You can clearly see that. Now, the original value of DB scan, okay, here. Yeah, the gain is this. The DB scan is we take 1 epsilon as 1. Of course, when you take 1, it's going to like cover the whole data set. The data set is living between -1 to 1. Okay. And then 5 nearest neighbor we're considering. So next is that we're going to we're going to compare, right? So originally it was 1, 5. Next is we increase the overlap. Yeah, we still keep the same number of cover, but we increase the overlap. Original was 0.10, which is 10%. Now we have increased to 15%. Right? And then for epsilon, I've now reduced to 0.2 epsilon, and then the same minimum sample, which is 5. So I end up getting a more, of course, when you reduce the epsilon, you will be getting more clusters, right? You'll be getting more clusters. In fact, when you overlap, you're going to get more edges. Okay. Now let's see. Right. So for the first, this is the first data set. The first data set with epsilon this 0.2 and then minimum sample 5. It is just one cluster. Whereas the next data set, that next data set, this is the next cover actually. This is V1, if you remember. This next cover is V2. V2 now, since we are using epsilon 0.2, it is broken into 3 clusters, as you can see here. 3 clusters. Cluster 1, cluster 2, cluster 3. Smaller epsilon, more clusters. Same goes to the next V3. For V3 as well, as you can see, this is one cluster now. Yeah, we have 1, 2, 3 clusters as well. 2, 3 clusters. Same goes to V4. And then finally, V5 is still intact as one cluster, right? Here V4, we have 3 clusters too. So we end up encoding the bigger circle as a proper circle. Circle means here, so one cycle. Whereas another one, the smaller one, smaller circles is now represented with the one connected component. So we have actually 2 connected components as data, and then we get to see the structure also. Right? Of course, the smaller one, the structure is not so prominent as a cycle, as a loop. Okay, so this is what we end up getting. Of course, each, as you can see, like for example, this points here, right? Let me clean it up a little. The points, right? We can encode the graph that we obtain with some information, right? For example, right? For example, let's say take this point. So in order to color the note, I can color the note based on, for example, the descriptive statistic. Take all these points, take the mean value. So I can color it based on the X mean or Y mean. If I take X mean, it's going to be very little difference. Y mean, oh, there is a range of differences, right? So I can color based on the mean values or some sort of like maximum value or standard deviation. Or I can also control the size. Usually the size is controlled based on the number. For example, here, yeah, here it's huge, right? The numbers are huge. So if the number of samples are huge, so probably I want a bigger circle to represent that number. Right? For example, here you see it's slightly bigger as compared to this one here. So this number is lesser as compared to this collection of these numbers in between. This number between is now encoded by this vertex, whereas this on top here, probably this, the last one here, a little, probably the smaller one. Yeah. So it has been annotated with color and size. So you can choose accordingly. For example, here, I colored based on the original label, just two colors. Big circle has one color, smaller circle has one color. So it can code nicely. The smaller circle gets a yellow corresponding to the one the inside, circle inside. Whereas the outside, the other one outside is in cream. Okay, so this is an example of a lens, of a mapper graph. Okay, with a different setting. So if you compare both, right? If you compare both, so originally we had, okay, we had 10, so now I've increased to 15%. So DB scan is like 1 here, so now I've reduced. So the number of clusters has increased, the network is more prominent, you get to see more structure. So you get to control actually. Yeah, so these are the different setting altogether. A different lens, see, oh, lens, so the last one I'm using both X and Y. The rest is like same lens, X, yeah, X, X, X. So I'm also controlling different intervals here. For example, I use different intervals. I have to use different overlaps. Yeah, for DB scan, I'm using different. You can, in fact, use a different cluster altogether as well. Okay, right. And then what you can see, it's the mapper algorithm itself is stable. Stable means slight change of the setting here. You get to see slight change of the structure. So the structure is somewhat, of course, the original structure was a two circle. So you get to see, like, well, one circle, one big circle is the prominent circle. You get to see the loop. Yeah, the loop is there. The so not so prominent circle, the one that's very small ones. So either it is showing itself by a flare or by a connected component. Yeah, as you can see, right? So this is how we then infer your data. So of course you get to investigate. You can directly investigate from vector algorithm. Okay, so more examples. Right, so this is here example from again from Frame, the founder of map algorithm. So they used this in the same paper actually with a 50% overlap. They used some sort of a distance metric, right? So in which you get to see, right, the left and right hand side, the same horse with a different movement. Of course, it encodes the same graph. The graph has a similar pattern. So human, this guy here is a bit like showing upset face here, whereas the normal face, again, the shape stays the same, right? And of course, here the last one here, an elephant, different movement. Again, the shape is the same. In fact, that is what we want, right? Another example here, the topology of politics. right? This is of course US. So originally in 2009, this is how the network looks like. So graph, mapper graph. This is how the network looks like of uh, two main party, Republican and Democrat. So in 2009, it was like this. If you draw a PCA, this is how it looks like, right? Whereas if you draw the mapper graph, you get to see the whole graph, right? So the mapper graph, of course, it has got more information that you can see. So originally it was just like one connected component, and then there are small ones. These are actually, the red ones has two connected component and etc. Whereas Obamacare, when Obama was in charge, he was the president, he proposed something called Obamacare, which really needs a lot of money, right? So a lot of, then once that was like introduced in March 2010. When he introduced that, you see how broken they are. There are many groups, subgroups, right? Which is not good for a party, right? So both the parties were probably having different ideas. In fact, within the party, they were having very different ideas. So it broke down into many smaller connected components. Yes, in 2010, when Obamacare was introduced. In 2011, it was like that all as well. But of course, in 2011, like more agreeable parties, so lesser connected component. So this is how you can take your data and then do inference, right? This is yet another example, the topology of basketball players. So you get to see, based on, of course, there are many features. You collect the data of each basketball player, and then you draw. So you get to see the role of players, how they are scoring, right? So how they are like protecting, being a scorer, and also being a defense, right? So right. So the takeaway is mapper graph has the following advantage. First, it's flexible. It's a super flexible. Yeah, it can be applied to any kind of data as long as the data, from the data, you'll be able to get some sort of distance or some sort of like kernel in which you are going to use as a filter function. Next is it is scalable. Scalable simply means is that, of course, you can use the code, you can use for different data set. In that context, is scalable as well. Or you can use for smaller data set. You can also use for like huge more rows. You add more rows, more features, you can still push it in and get your data. So it is scalable in the form of data itself and also the code itself. Interpretable, visually you get to see, and then you get to map, right? You get to map who is like which structure encodes what feature in the data. And then parameter exploration, where of course when interpretable, you get to also see, you get to understand the data very well, and then you get to make a more proper selection of the feature, right? And here, sorry, the exploration here simply means is that it has got so many free parameters. Yeah, so many free parameters where you can just choose and change and switch. So it takes a bit of time as well. So of course, if you know your data well, you'll be able to do it faster. If you don't know, you can get to like do experiments, whichever that you feel like, okay, a nice proper setup for the production of your mapper, and that would be it. Okay. Integration with other techniques or data analysis techniques. Again, for example, cluster, right? Any type of clustering method you can use. You can use any type of dimensionality reduction, right? A variation will be a ball mapper. Ball mapper, it's more lesser free parameters. Sometimes too many parameters, you don't know what to control. If such a thing occur, then you just opt to ball mapper. There's also a mapper algorithm, but not much flexible. But you just put your data in there, and then you quickly just get one mapper out of it. It is why it was done. It was created by Powell Blotko, right? One of my friend, colleague. All right. So with that, thank you very much. So next lecture would be on persistent homology. And now, okay, so you can start thinking of your data and then play with the code and create your own mapper graph. Thank you.